Welcome back to another lecture video. In this video, we're going to be taking a look at related rates problems. This is starting in section 3.9. So if you go to the section 3.7, 3.9 page, we looked at rates of change, lesson 14 on Friday. We used a little bit of Desmos in that. I've linked the Desmos file for it. And here's a copy of the lecture from Friday. There's also a couple of rates of change videos that are just extra videos for you to watch if you get a chance. We're going to be focusing today on related rates. There are two related rates videos here for you to watch, but we're going to record basically what we would have done in class over this topic, a couple of questions related to what's called a related rate. So let's take a look at it together. We're going to start with kind of a checklist. All of our problems are going to go through this checklist. We're getting into the part of the course now where we have word problems or problems associated with applying the derivative, applying all these different things we've learned so far in calculus. So we're going to kind of go through a checklist just to make sure that you're progressing through these problems correctly. But I want to talk briefly about what is a related rate in general. You can think of it this way. Suppose that you had a cup, and there's a kind of a water spigot here or a faucet, and you've got water flowing into the cup or into the bowl or whatever it happens to be. The rate at which water falls out of the faucet is related to the rate at which water fills up the cup. And what I'm really talking about is the rate at which the height of water in the cup fills up. So these two quantities are related. So in this unit, we're going to be dealing with problems similar to this, where we know the rate at which one object is changing and it has an effect on another object. There are many different examples of this in the real world. You can think of the rate at which the pistons fire in an engine. You can think of that as being related to the rate at which the wheels turn on a car. Right? Those two rates are related. The faster the pistons fire in an engine, the faster the wheels will turn on the car. Those two things are very much related. So we're looking at some way to sort of quantify the relationship that different rates have. Now, all of our problems, we're going to go through a checklist similar to this one. I'll number things, steps 1 through 5, as we go through the problems. Every problem is going to involve us drawing a diagram. We're going to label quantities in there. There's two quantities specifically that we're looking for. The two quantities that we're looking for is specify the rate of change that you're looking for. In other words, that's the rate that we want, and record all other given information. That's the rate that we're given. So we're going to always list down a wanted rate and a given rate. That's after drawing the diagram. And then we're going to find an equation that relates the wanted rate and the given rate. So some mathematical equation that relates these two quantities. We're then going to use implicit differentiation. So if you don't know how to implicitly differentiate, you're going to have to be able to do that to solve these problems. If you need to go back and review it, consider the material in section 3.5. Once we implicitly differentiate our solution, we'll be able to find the rate that we want. It'll pop out when we do the differentiation. Then we'll be able to plug some numbers in and get the final answer. So I'm going to repeat these 5 steps each time and talk about them as we go through the next problems. I've got 4 examples planned today, and I think another 4 examples planned for Wednesday. So you'll have several examples of related rates by the time we get to the quiz on Friday. All right, so first question. Suppose we are 30 feet from the side of the road. So here's the roadway. 30 feet from the side of the road is a police officer. The police officer is shining their radar gun at a car that's passing on the road. We know that the car is approaching at a rate of 80 feet per second, and when the car is 50 feet away, from the police officer, we know that the movement or the speed here is 80 feet per second. If the speed limit is 65 miles an hour, or that's approximately 95 feet per second, what I want to know is, are we speeding? So I've drawn the picture for you this time, but I won't do that in the next examples that come up. But this is always step one. Step one is to draw a diagram and label the sides. Since this distance is always 30, it doesn't make any sense to give a variable for this side. This side is x, this side we'll call d. One of the things I want you to understand is the rate at which things are occurring and whether they're positive or negative. So let's start with d dt, the rate at which this distance between the car and the police officer is changing. That quantity is negative because this distance is decreasing. Remember, a negative derivative means decreasing. Similarly, dx dt is also decreasing in this problem because the distance from the car to this point in front of the police officer, that distance is decreasing over time. So your second step, once you've drawn a diagram, is to list the rate that you want to find and the rate or rates that you're given. So the rate that I want to determine is my rate along the road. So this rate right here, I want to know dx dt at a specific time, and it's at the time that d is 50. So in other words, at this moment in time, what is my speed along the road? Right? Now, what are we given? Well, we're told that the radar sees your car approaching at 80 feet per second. So the radar gun says that the rate of change of this distance is equal to 80 when d is 50. In other words, it's actually negative 80 because remember I said that this distance is decreasing. So this is negative 80 feet per second. That may seem a little weird at first, but the radar gun, the length of this is changing at a rate of 80 feet per second according to the question. Okay, so here's what I have to do. This is step 3. I have to create an equation that relates the two variables here. So the x variable and the d variable. So if you look at this diagram, what mathematical relationship is shared by d and x? Now remember, d isn't always 50, so I should think of this side as being a function of time, just like x here is also a function of time. Both of these quantities are changing over time. So if you want to relate d of t and x of t, since this is a right triangle, you can use Pythagorean theorem. So we know that x squared plus d squared, plus 30 squared equals d squared. And you may be tempted to solve for x since we want to know dx dt, but resist the urge to do that because all you want in step 3 is the equation, and trying to solve for things algebraically in this step is going to probably lead to you making mistakes in step 4. So step 4 is taking the implicit derivative of both sides. Now you take the derivative with respect to the quantity that's changing in the problem, the independent variable. In this case, the independent variable is time. Time is what causes the car to move along the road. Time is what causes x and d to shrink in size. So if I take the derivative with respect to time of both sides of this equation, remember x and d are both functions of time, so this makes complete sense to do explicitly. X is a function of t, d is a function of t. So when I take the derivative of the left-hand side, the derivative of x squared is 2x times dx dt. The derivative of 30 squared, where 30 squared is a constant, the derivative of a constant is 0, so you get plus 0. Then if I take the derivative of the right-hand side, the derivative of d squared is 2d times the derivative of the inner function with respect to time because of chain rule. So this is correctly differentiated implicitly. Each time I take the derivative of a variable, I have to multiply by the derivative of that variable after I take the outer function's derivative because of chain rule. So it's at this point that I've done my implicit differentiation. Let me go ahead and clean it up just a little bit. And so I'm almost done with this problem. The only thing I have left to do is step 5. Step 5 says solve for the rate that you want. So we want to know dx dt. So I'm going to solve for dx dt. So I'm going to solve for dx dt, but not at any given time, at precisely when this distance is 50, because I want to know what is my speed along the road at that precise moment in time. So solve for dx dt when the distance from the car to the police officer is 50. So I've got 2x dx dt equals 2d dd dt. And let's think about what pieces of this we know. The triangle, at the moment in time that this car right here is passing in front of the police officer here, we know that this is 50. We know that this side is 30. We know this is a right triangle, so I can figure out exactly what x is at that time as well. X is 40. This is a Pythagorean triple, right? A 3, 4, 5 triangle. So if this side is 30 and the hypotenuse is 50, I know this length, the x length, the road length, is 40. So when d is 50, this is what the triangle looks like, which means x can be replaced with 40. dx dt is what we're solving for. So we want to know dx dt when d is 50. On the right-hand side, you have 2 times d, but we're looking at it when d is 50. And then you were given in the problem, you were told that the rate at which the distance is changing at that moment in time is negative 80 feet per second. Remember, it's negative because the distance d is decreasing. So d dt is negative 80. Okay, we're almost done. I can then solve for the rate. And so we'll just throw that into a calculator real quick. And if we calculate all those values, it will give us negative 100. And this would be feet per second. Now keep in mind, it makes perfect sense that the answer is negative 100, okay? Because this distance is decreasing over time, and that's my speed along the road. So the rate of change of this distance should be negative. We should be closing in on the police car's position, thus decreasing the length of the x distance. So what I want you to understand then is our speed is 100 feet per second. This is greater than the allowable speed of 95 feet per second, which means we are speeding. Because you were told in the problem that the speed limit is 65 miles an hour or 95 feet per second. We're actually traveling at a greater rate, 100 feet per second, than the allowable speed limit. So we are, in fact, speeding. All right, this is a good first example for us. It brings together all 5 steps. You've got the diagramming step, listing the wanted and given rates, relating the 2 quantities that are in the wanted and given rates, differentiating the problem implicitly, and then solving for the correct rate at a specific time. Now understand that when I say at a specific time, I don't actually have to calculate the value of t. I just need to know that it corresponds to when d is 50. We're going to see a lot of examples of that coming up. All right, so next example is very similar. We're going to draw the diagram together. So this is step 1. You've got a camera do my best to draw a camera here. So you've got a camera that's located 50 feet away from a straight road, along which a car is traveling at 100 feet per second. So if we call this distance x, then we know that dx dt is negative 100 feet per second, just like on the previous example. If the car is traveling toward the position of the camera, then we know that this distance is decreasing at a certain rate. So this quantity here, the hypotenuse, is, they don't give us a distance of it, but they do tell us that the camera is trying to keep pointed at the car at all times. So the camera is looking at the car, and as the car passes along, the camera rotates to keep the car in frame. So there's a certain angle, I'll call it theta, that changes over time to keep the car in frame, and the position of the car along this highway, x of t, the position is decreasing. Now, we don't really need to know the hypotenuse just yet, although we may discover along the way that we need to know it for some reason, but right now I'm just going to kind of leave it blank. So if you look at what the car is asking, it says in radians per second, how fast is the camera turning as the car passes closest to the camera? So what I want to know is the rate at which theta of t changes when the car is here. In other words, the car is traveling at a high rate of speed, the camera is turning as it does. How fast is the camera turning when the car reaches the spot directly in front of it? Okay, so let's put this into a little bit of mathematical terminology. So step 2 is tell me the rate that you want to find, tell me the rate that you are given. Well, the rate that I want to find is how fast the camera is changing, so that's d theta dt. Now there are a couple of different ways to think about when I want that rate. I could think of it as when the car is here, which means when x is 0, right? There's no distance there if the car is there. So I could think of this when x is equal to 0, or I could think of d theta dt when the angle is completely closed down, so theta would be 0. Those are both at the same time, even though we're not calculating what time that is. These are the same thing. I just don't know which one's going to be more useful to me later. Is it going to be setting x equal to 0 that I want to do, or setting theta equal to 0? So we'll just have to wait on that and see. The given information is we're given this rate here, so we're told that dx dt is negative 100 feet per second. Okay, so here's what this problem basically comes down to. So we'll call this step 3. This problem comes down to, can I relate theta and x on this triangle? So here's where knowing trig helps. Here's where knowing geometry helps. You're going to run into several things from past classes that you need to have retained and bring forward in this class to have success on a lot of these problems. So I want to relate theta and x. If theta is the angle, x is the opposite, and I also know the adjacent side to theta. So tangent seems the most reasonable here. If I said, okay, tangent of theta is opposite over adjacent, opposite is x, adjacent is 50, so this tells me that 50 tangent theta is equal to x. And keep in mind here, both theta and x are functions of time. So on step 4, when I go to differentiate these, I should differentiate with respect to time. So differentiate tangent of theta and differentiate x. So the derivative of tangent, if you recall, is secant squared. So on this left-hand side, this would be 50 secant squared theta, but then I have to multiply by theta's derivative. And over here on the right, the derivative of x is just, we would say, dx dt. Okay, so I've done my differentiating. Then step 5, I'm going to solve for the wanted rate. The wanted rate is d theta dt. Now I have to think, is it going to be better to use x equals 0 or theta equal to 0 here? And you can see that I don't have any information about x anywhere in this problem after I've taken the derivative, but theta appears right there. So I want to solve for d theta dt when theta is equal to 0. So I would get 50 secant squared 0 d, not theta, 0, when d theta dt is at theta equal to 0, is equal to dx dt. Well, dx dt is negative 100 feet per second squared. That was the given rate. So secant, if you recall, secant of theta is 1 over cosine. So secant of 0 would be 1 over cosine 0, and cosine of 0 is 1. So I've got 50 times 1 times d theta dt is negative 100. So d theta dt, if I solve for it, when that angle is all the way closed down, that's given to us by negative 100 divided by 50, which would be negative 2. Let's be careful on the units here. The units for theta are radians. The units for time are seconds. So this is negative 2 radians per second. I think that's all we need to say about that. So we know that in order to keep the camera in frame, we know that as the car passes this point, the camera will be rotating at a rate of negative 2 radians per second. Once again, the negative makes sense here because the angle is getting smaller. As the car passes in front of the camera, the angle closes down, so the angle theta is getting smaller. This is actually a real-world problem, by the way, because if you've ever watched movies where they have sort of high-speed chase scenes or they have, fast-moving action, they don't actually have people hold those cameras and actually film it by holding the camera. They actually mount the camera on these special rigs that they can set the angle change, so it'll move the camera itself at whatever rate it's programmed to. So they'll have to go in and calculate like how far away is the action occurring, how fast is everything moving, and then they can program it to actually keep the camera in frame with the action without having any humans actually rotating the camera manually. So this kind of problem is pretty pervasive in the movie industry. So it's just one example of where related rates can help you determine things. All right, third example here. This is kind of related to the example I talked about at the beginning. We have a conical shaped tank. So a cone-shaped tank. Think of the tank as being kind of like this. Not very practical, but for the purposes of this problem, it'll do. But we have a conical tank. The radius at the top is 4 feet. The depth is 10 feet. It's being filled with water. So we've got this thing being filled with water at a rate of 2 cubic feet per minute. So sort of a true-false question here I want you to think about, and you can pause it if you kind of want to think about it and give me an answer, but the water level in the conical tank is rising at a constant rate. In other words, is the water level in this tank, as it's being filled, the water level goes up? Is the rate at which the height is increasing, is that constant? So I'll give you a second to think about that. All right, if you haven't paused yet, please do so, but the correct answer here is false. The water level in the conical tank is not rising at a constant rate. If you consider it, there's much less volume needed down here, so it's going to rise very quickly at first, and then it's going to not rise. The height of the water won't rise quite as quickly once you get up toward the top. If you were filling a cylindrical tank, the answer to this question would be true, because no matter how quickly the water comes into the cylindrical tank, because the cross-sectional area of the tank is the same, the height at which the water rises would be the same. So for this example, it would be false, but for this example, it would be true. So it depends on the shape of the tank. But we're going to be dealing with the conical shaped tank, which actually makes this problem a little bit interesting, the fact that the rate at which the height increases is not constant. So the goal of this problem is to find the precise rate at which the water's height is rising when the tank is 5 foot full. So when the height of the water is 5 foot. So let me draw a good diagram here, try to label everything we can. That's step one. All right, so there is our conical shaped tank. We have water coming in at a rate of, let's see, we were told that it's at a rate of 2 cubic feet per minute. So 2 cubic feet per minute, that's the rate at which water comes in. We know that we have a radius. The radius at the top is 4 feet. So we know that the radius here, this distance, is 4 foot. We know that the height of the entire tank is 10 feet. And just to make sure that we have some variables to work with, and honestly this is the hardest part of the problem for most students, is just imagining what these variables are. There are 3 variables that are involved in this problem. You've got the volume, you've got the volume of the tank, and it's related to the radius. So I can think of this as R, the radius changes over time, and the height also changes over time. So this quantity right here, h of t, that quantity is the water's height. It's constantly changing. This distance is the radius of the water as it's filling up the tank. That is also constantly changing. And so I'm just thinking about what this would look like in general. So here's the water. What would this look like in general inside this cone? So the volume of water in the tank is also changing. So these are the 3 quantities that are in some way related in this problem. The volume of water in the tank is going up. The radius will also be going up over time, because you can see the radius distances are getting bigger. The height will be going up over time. And so this is a good picture. It gives me an idea of how all these different things are related. So step 2, I should list the rate that I want to find and the rate that I am given. So the rate that I want to find here is the precise rate at which the water's height is rising. I want to know dH dt. Specifically, I want to know that rate, the rate at which the height is changing when the depth of the water is 5 foot. So dH dt when the height of the water is 5 foot. Now, what am I given? Well, the given rate here is a little tricky for some students, but it's actually volume. And this is why, if you just had written down R and H, you might have overlooked this. You were told the rate at which water enters the tank, which means you know the rate at which the volume in the tank changes. So if the water enters the tank at a rate of 2 cubic feet per minute, then you know that the rate of change of volume of water in the tank is plus 2 cubic feet per minute. It's adding an additional 2 cubic feet every minute of volume to the tank. Okay, so here comes step 3, which is the trickiest part of this problem. Requires you to remember something from geometry class in high school. I want to relate 3 variables in this problem. I want to relate, well, technically, all I need to relate is V and H. But it's impossible to do that without involving R. So can you think of a way to relate V, H, and R? Well, this involves the geometry formula for a cone. Now, on a quiz or on a test, if I was asking you to look at some geometric figure, I would probably tell you what the formula is for the volume or the area or whatever. I don't expect you to have all those memorized, although it probably would be nice if you knew it for a cone. It's a pretty standard figure. But the volume over time in a cone is 1/3 pi r squared times the height. So pi r squared is the area of the base times the height. And the tendency for most students is to just go ahead and plug in R and go ahead and plug in H, and that'll give you the volume of the entire tank, but it doesn't, if you try to differentiate that, you're just going to get 0 because everything in that problem will be a constant. So never plug in values for variables until after you have completed step 4, which is the implicit differentiation. Now, here's what makes step 3 on this problem a little trickier. We have a equation which relates volume, radius, and height, but I can't take the derivative of this as is, because if I did take the derivative of this, I would get dr dt, and we are not given any information about dr dt, nor do we want to find dr dt. So if we were to take the derivative of this, we'd have a product rule here. It would be messy. We'd end up with 2 rates, dh dt and dr dt, and I don't know anything about dr dt. So what I want to try to do here is, can we relate R and H so that V depends only on H? In other words, can I relate the variables R and H so that this volume formula is a function of just H? And the answer is yes. This also requires you to know a little bit of geometry from high school. If I just draw the picture here of the situation that we have, so this is sort of I'm going to top down, I'm going to cut down the middle of the cone all the way through. So this is what it would look like. This distance is R. This distance is H. We know the entire distance here is 10, and we know that the radius distance here is 4. So this is the situation we find ourselves in, and honestly I just need to look at 1/2 of it. So here, I'll just draw it this way. So this is half of this is the middle cross section of the cone, only half of it. I know that this distance here is H, the other distance is R, and then the total height is 10. So this is a perfect setup because this is a right triangle, this is a right triangle, you have a small triangle, you have this small triangle here embedded inside this bigger triangle. This is something called similar triangles. I don't know if you recall this from geometry or not, but this is set up perfectly for a similar triangles relationship. So similar triangles states that the base compared to the base, so the base of the little triangle over the base of the larger triangle, is equal to, the ratio of these is equal to the height of the little triangle over the height of the bigger triangle. So that relationship between R and H exists, which means I could easily solve for R. R would be 4/10 H or 2/5 H. And the importance of that is I can take this volume formula and rewrite it as 1/3 pi R, but here I have a description for R. This would be 2/5 H squared, because this is just R, times the h, which is already there. So this is 2/5 squared is 4/25, times 3 would give 4/75 pi. And then you notice you've got an h squared and an h, which gives h cubed. So I now have the correct step 3 completed. And when I say correct, I just mean I correctly have volume written in terms of height. In other words, I'm supposed to relate height to volume, and I now have an equation that relates height to volume. So I can continue on to step 4 now. So in step 4, I want to differentiate with respect to time both sides of this equation. If I do that, I will get dv dt on the left-hand side, and I will get 4/75 pi times 3h squared dh dt, which is 4/25 pi h squared dh dt. All right, so I've done the differentiating now. And so step 5, I want to solve. Let's go back up and take a look at our rates. I want to solve for dh dt specifically when the height of the water is 5 feet. So solve for dh dt when h is 5. So question is, what is the volume? Well, that was the given rate. The volume increase at a rate of 2 cubic feet per minute is equal to 4/25 pi h, so this is when h is 5 squared times dh dt when h is 5. So the 5 squared and the 25 cancel, and so it looks like you get 2 divided by pi is the rate of change of the height when h is 5. 2 divided by pi, so let me look real quick, divide those. 2 divided by pi. Well, I don't have it here, so we could go to Desmos and find it, but this answer is fine. Height is measured in feet. So this would be feet per unit time. So feet per, I think it's minute in this problem, right? The units are, yes, minutes for time. So the water level is rising at a rate of 2 over pi. Pi is about 3. So 2/3 is about 0.6. This will be a little bit smaller than that. So like 0.58, something like that. 0.58 feet per minute is the rate at which the height in the cone is changing. So that was a considerably more complicated example from start to finish than the other ones have been so far. The main complication here occurred in step 3. When I tried to relate the variables v and h and involved another variable r. Oftentimes this will happen in related rate problems, and when it does happen, you should look for other mathematical relationships to relate r to h so that you can have a formula that depends only on h like we were able to come up with here. So you need to be very careful when going through these problems that you are following the steps that I've outlined here. All right, one final problem to take a look at for today, and then we'll do several more examples on Wednesday. Suppose you have a Ferris wheel with a radius of 10 meters, and the Ferris wheel is rotating at a rate to where it makes 1 complete revolution every 2 minutes. How fast is a person rising? How fast is the height of the person changing when the seat is 16 meters above the ground, above ground level? So we're going to round our answer to the nearest 1/10 of a meter per minute. Okay. So I'm going to start with a picture. See if I can draw a nice circle here. All right, so this is our Ferris wheel. I'm going to make a couple of simplifying assumptions here. Since we weren't told otherwise, I'm going to assume that the Ferris wheel is sitting at ground level. So here is ground level. Now, honestly, there would be a little bit of a distance here because otherwise the Ferris wheel wouldn't be able to return. But just, you know, unless said otherwise, this is what you should assume here. So it's rotating at a rate of 1 revolution every 2 minutes. It has a radius of 10 meters, so the distance from the center of the Ferris wheel to ground level is assumed to be 10 meters. I am looking at how fast a person is riding when their seat is 16 meters above the ground. So let's say, just for sake of argument, here is the Ferris wheel seat. Here's the person in the Ferris wheel. Their vertical distance is increasing, right? So their dH/dt is increasing, but I want to figure out how fast is h of t increasing. So I need to figure out the rate. And the rate at which their height is increasing is related to the rate at which this angle is rotated. Now, I just want to I probably don't write that theta angle down just yet because we're about to change it. So if I left it in this form, then what you would want to try is you would want to try to say, okay, well, here's the height of the person. So this, I'll call this h, changes over time. Here's theta, theta changes over time. Here's the problem with setting up the variables in this way. If you set up the variables in this way, then you have to be able to relate this quantity h to this quantity theta in order to solve this problem. That is difficult to do in this current configuration because you probably don't know trig well enough to relate theta and h. It would involve law of cosines, most likely. There's other ways to do it, but that's probably one of the better ways that you could do it, and that's not how I want us to handle it. So this is h, but rather than focus on theta being this entire angle, how about we do the following? So I want to try this instead. And this is what's difficult about this problem, is getting it set up in a way that makes the problem easy. We know that that length is 10. We know that whenever this is at a height of 16, that's going to form a right triangle. And we know all about right triangles inside of circles. That's what all of trig is about. So we know that entire length of that side is 10, which isn't going to be a big deal. And so rather than us look at the entire length here, we know that this distance is going to be 10. We know this distance would be another 6. So I'm thinking of this distance as being my h of t. And we want to know when h equals 6, because this distance is already 10, which gives us a total distance of 16. If I called this height h, then when h is 6, we would have the distance of 16 that we need. And I want you to see how big a change that makes to working on the problem. So now if you go to step 2 and list the rate that you want to find, you want to know dH/dt, and specifically you want to know dH/dt when h is 6. So how fast is this vertical distance changing when they're 16 feet above the ground? So when h is 6. You are given the rate at which theta changes. So theta is making 1 revolution every 2 minutes. Now you should be very careful here. There are different ways to talk about this. Let me just do it this way. D theta dt, you might want to say 1 revolution every 2 minutes. The only problem with that is when you do calculus, you must always keep theta in radians. None of the stuff we do in trig or calculus works if you are converting to a different format. Okay, you've got to keep the angles in radians. So 1 revolution is 2 pi radians in 2 minutes. So the given rate that you want, d theta dt, is equal to pi radians per minute. That's the appropriate given rate and wanted rate. So we know this angle is changing at a rate of pi radians per minute. Pi radians is 180 degrees. So if the person was here, they'd go all the way over to here every minute, and then every 2 minutes, it completes a full revolution. Okay, so step 2 is complete. Step 3. And here's where we're going to reap the benefits of calling this h rather than calling the whole thing h, and calling this central angle theta rather than this bigger central angle. So given the picture we have, I want you to relate theta and h. Okay, so in order to relate theta and h, I have to think about the information I'm given. I know an angle, I know the opposite, but I don't know the adjacent. I do know the hypotenuse, because the hypotenuse is the same as the radius. The hypotenuse is 10. So I know opposite and hypotenuse, which means I should use sine. So the sine of theta is equal to the opposite over the hypotenuse. So I have something which relates theta and h. And once again, this theta is changing over time. Okay, so step 4, differentiate both sides with respect to time. So the derivative of sine is cosine times the inner function theta's derivative. Okay, distributing to h, the derivative of h, this will be 1/10 dh dt. So the derivative has been taken on both sides. And so step 5, I want to know this when h is 6. So I want to solve for dh dt when the height is 6 feet above center. So 16 feet total, but h represents the height above the midpoint. So when h is 6. All right, so here's the thing. I don't know this angle. So I can't plug an angle measurement in for theta. I guess actually I could find that angle, but it's actually more trouble than it's worth. The picture we find ourselves having at this point is a triangle that looks like this. This height is 6. This length is 10. This side I'll just call x. It's unknown at this point. Could we solve for it? Yeah, absolutely we could solve for it. If we think of this as a 3, 4, 5 triangle, then 3 times 2 is 6. 4 times 2 would be 8. 5 times 2 would be 10. So x is 8 in this picture. If you want to use Pythagorean theorem to solve for x, you could. But we know in this picture this x distance is 8. I know that I'm going to have to plug in something for cosine theta, and so on this triangle, cosine theta is adjacent over hypotenuse. The adjacent side is 8, the hypotenuse is 10. So when I go to plug something in for cosine theta, I should plug in 8/10. So solving for dh dt, I have 8/10 times d theta dt. Well, d theta dt was the given rate, pi radians per minute. So times pi radians per minute equals 1/10 times dh dt, which is what we want to solve for when h is 6. So if you just compare, I've got 1/10 and 8/10. So I've got 8 pi divided by tenths equals, dh dt has to be 8 pi. So if you solve for dh dt is equal to 8 pi. Now let's make sure we get the correct units. The units for height are, let's see here, the units for height are meters. So you've got 8 pi meters per. The units for time are minutes. So 8 meters per minute. So that is the rate at which the person's Ferris wheel seat is traveling upwards. That's the vertical rate of change. It's the rate at which the Ferris wheel seat is traveling upwards as the seat rotates around, when the seat is at a height of 16 meters. I mean, if you think about it, you know, your rate of change of height is fastest right here. You're going up the fastest right there. It starts out, your height doesn't change very quickly here. Now your height is actually increasing much faster here, but then it slows back down over here. And the other thing I want to say about this problem, it doesn't matter if we put the Ferris wheel rider here or here. Both of these are at a height of 16 feet. The math is identical regardless of if you put it over here. So this was a tricky problem because I think for a lot of students you would not have drawn the diagram this way, and that would have made it very difficult to get something that was easy to differentiate later on. So this example sort of serves as a warning that these problems can be really difficult if you do not draw the diagrams correctly. They can still be done, but they become much harder. All right, those are the examples that I have for you today. Those are the only things that I wanted to cover. We're going to take this topic a little bit slower than the others. You should be working a lot of problems, a lot of practice problems on this. You should be taking a look at the other videos that are available to you. We're going to do this again on Wednesday, and that should get you ready for the quiz on Friday over related rates. All right, y'all have a good day.